Okay, we'll briefly touch upon what is the pseudocode for the uniform cost search. Of course, it will not take a graph as input, it will take a problem definition, which includes your state class source as an object of the state class, all the action functions and the feasible action functions. And we'll do a search based on the same problem definition. So let's say that you already have a source object, which is given as a part of the problem definition. Now, what you need to do around over here is, of course, add it to a priority queue. So add source to priority queue with a priority value given as its G value. And of course, by that we know that the G value of the source is 0, the parent of the source is a nil, the action that I need to go to the source is also nil, the depth of the source, you don't really need it. If you need to store that as well, is again what is a nil. So that's the meta object, which this is the metadata which is associated with it. Now, typically there are two implementations possible. One is to create a node class which has attributes, the source state itself, the G value, the parent value, the action, the distance, the depth. The other one is to just take this G, parent, A and D as hash tables, hash maps, which are globally occurring. In UCS, you could take in whichever implementation that suits you. So I let you decide. And of course, along with that, I will also take a closed, which is initially empty. So that will be my hash map, which will tell whether a node has been processed or not. And let's call this thing as a frontier, of course. Now, why my priority queue is not empty? So why frontier is not empty? Simple implementation. All that I do is I extract S from frontier, which is the one which has the least priority values. And then, of course, all that I do is that I apply all possible actions. So for all feasible action A applied on S, I get the S dash, which is application of action A. And that's why I said that the input is not a graph. So I'm assuming you already have the feasible action function with you, which gives you the new state S dash. Of course, it's a uniform cost search, so I check whether I have rediscovered it with a better value. So if S dash is in closed, then of course I need to do nothing and I can just continue. On the other hand, if S dash is in frontier, now again that's a little thing. So how do you check whether a node exists in the frontier or not? Maybe just make another map for it, maybe make use of it that it'll have a set G value. So if S dash is your new node is in frontier and it has a better cost, so its cost will be given by G of S plus the cost in going from S to A to S dash. And again, I know that your problem definitions were complete. That means all these functions just exist. So that's a SEP cost function. Or of course, it's also true that if S dash is not in frontier, then the simple thing that you do is you calculate all these values. So you update g of s dash is equal to g of s plus c s a s dash, and you set parent of s dash as s. You set a of s dash is equal to s, the action that brought you from s to s dash, and of course the depth of s dash is equal to the depth of s plus 1, and you add s dash to priority queue with priority g of s dash. Now, you would observe that there is one caveat over here. Normally in theory and in books, we write it down. We break these two conditions, this one condition into two conditions. So we say if it's not in frontier, then insert in frontier. And if it is already in frontier and it has a better cost, my bad, then you just update it inside the priority queue. What I've seen for long is that people take in standard libraries for priority queue, so there's no way they can get in the standard library into the priority queue and change its value. It's possible in a heap, but not if that's not your own implementation. So people cannot really get pointers to the nodes inside and update it up. So not a correct code, which is typically the one which is mostly used. Instead of updating the node in the priority queue, you reinsert it afresh. The old one will not cause any damage, will not cause anything, because the new node is the one which will give the better cost, and always before updating the cost you check for the old one. So that's a more practical one. Another thing for the one people who first start off with making node, then realize that this parent thing is actually a pointer. Now, that means they'll have to make a pointer and update and maintain a pointer, and people are like, no, there's a library which just implements a hash map, so just let's use that library, and then the nodes become the hash tables and hash maps, so that you need to avoid pointer over here. You can use that for the uniform cost search, no matter, but then of course, if it was a depth first search, you have to deal with pointers for the parents, because you cannot just take global visited, global colors and global maps. The memory will grow with size. So everything has to be strictly within the node. And then of course you will have to maintain in such a parent as a pointer. So just some quick code things that people usually like me to discuss. And of course, if it was a graph implementation, I will add stu closed over here. And for the completeness of it, even though it is obvious, so let's just mention if goal test is passed by the state S, then return compute path from S using everything that you have used so far. And of course, if nothing happens, then you return no path found or null as your plan. So that's a uniform cost search algorithm as one little pseudocode. Now, one thing that you need to be sure of is that if it's already enclosed, you cannot calculate, you cannot find it with a better cost. So I short circuited around over here rather than checking if it's still with a better cost. There's a guarantee that will never be with a better cost. So I just short circuited that over here in this implementation. Now, I don't say whether follow the node route where you actually create in nodes, or you follow this wonderful route where G parent A are all global hash maps and everybody uses that for accessing whatever they want. If you do use the nodes, this is where it'll get a problem, because you need the cost of the old node that is already in the tree, which is information stored at node, so it also needs to be globally present as a hash map. And therefore people say that, okay, when one needs to be a global hash map, let everything be a global hash map. So in terms of data structure not written over here, a typical implementation everybody does is G is what is a hash table or a hash map. It takes a state S in its encoded form, whatever class object you had it, and returns its G value. Similarly, parent is a hash table. It takes a state as input, gives a state as output. So hash map between state and state. Action is of course a state as input and typically a string, which is just an action name as output. Sometimes instead of the path in terms of state, people say, give me the sequence of actions. So you just return the string of actions. D is of course the depth. It's a hash map that maps the state to an integer. The priority queue library default implementation will do. All the others are what are standard function. This thing is not something that will be there in a library implementation of a priority queue, but you can just say that if the hash map of G, or if the map of G contains S dash or not, and that's how you can get that. So it's a pretty easy implementation. The only caveat is, please do not use this kind of an implementation in a depth first search, because in depth first search, because it's a tree implementation, you have to take a node. No global hash maps like this are allowed. Doubly ensure, otherwise you'll get a memory leak. You'll not know that your algorithm theoretically is linear memory, but in reality it's taking exponential memory until your system breaks down, provided you run it that long. So there you have to go with the old approach given in any book, where you create a node class which has a state object, which has parents, everything. The parent in case of C will actually be the state star pointer, and in case of Java, of course, it could be references. And if it was a depth first search, please make sure that there is no global variable which is just accumulating like G is doing over here, just accumulating memory. Parent is accumulating memory, so no global hash map if it was a depth first search. So that's all from the programming perspective.